Let us come back to the area between curves. We discussed area between curves already in the previous calculus class, but here I like this opportunity to introduce a little bit a different notation, which I find is actually much more intuitive than this cumbersome sum symbol here, right? Remember we define everything with the Riemann sum. Sum I is 1 to n, f of xi star minus g of xi star delta x. And then the xi stars are representatives of these little intervals. So here is a new way to understand this, and maybe also a new way to write this down. Let's first look at the two curves. So here I plot two functions, and then instead of calling them f and g, now I just call them f top and f bottom. And what the Riemann sum does is it looks at a very typical element, at a very typical rectangle, which is right between those two curves. So maybe this one here. And now I call this small line segment, I call this dx. So dx is a small piece of the x-axis. And I call this a small line element. Then I can easily compute the area by multiplying this small line element with the distance here from top to bottom. So then the area here in this little bit I call dA, where dA is a small area element. And so then I'd simply write dA, the small area would be f top minus f bottom, and then this times the width, and the width is a small line element, so it's dx. So dA is f top minus f bottom times dx. And then to find the entire area between the two curves, I just add up all these little dAs. And adding, as we have seen, is actually integration. So what I do is I write a to be the integral over all these little dAs, these small area elements. So I can write this to be f top minus f bottom in brackets dx. And here you go. So I have an alternative version to write down the formula for the area between curves. Okay, so this should compare to this, and it does really nicely. But here now I use the notation with the small area element and the small line element. Okay, let's do this in an example. Here I have two functions. I would like to look at them between 0 and 6. One is 2x plus 5 and the other one is x squared plus 2. Let's plot those. 2x plus 5 is a straight line starting at 5 and having slope 2. So let's call this 5 here. The other curve gx is x squared plus 2, so it's starting at 2. And then we have a parabola, so maybe something like this. And you can figure out they have an intersection point exactly here at 3. And then we are integrating to 6, so let's say this top here is about 6. Now you see the area between the curves consists of two parts, a1 and a2, where in a1 the first function f is the top function. However, in a2 the second function g is the top function. And we saw that for the area between curves we always do top minus bottom, so we have to flip the orientation once, and we flip it at 3. So if we are in the first interval from 0 to 3, then we write the area element dA, f top minus f bottom, times a small line element dx. But now f top will be the f function itself, so 2x plus 5, minus, and the bottom function is g, in this case, x squared plus 2, all this dx. And so then we can figure this out. It is minus x squared plus 2x, and then we have plus 3, all this dx. So that happens in the first bit for a1. In the other part, if x is between 3 and 6, then we have the same general formula. dA is f top minus bottom, but the functions have switched. So now the top function is a g. So then we have x squared plus 2 minus the bottom function is f, 2x plus 5, in brackets, so that the minus sign carries nicely. And then this is, we get x squared and then minus 2x and minus 3, all this dx. And then the total area would be a1 plus a2. So then the area would be the integral from 0 to 3 dA, which is for the one case, plus the integral from 3 to 6 dA, which is for the other case. Write it out, we get integral 0 to 3 minus x squared plus 2x plus 3 dx. And then the other part plus integral from 3 to 6, x squared minus 2x minus 3 dx. Okay, so we also got the integral written down. We did not use the cumbersome Riemann sum, but we did use the dAs and dx's as a little bit different notation than we did before. Let us compute this integral here. So then we can just integrate. These are polynomials. So we integrate the first one, which is minus a third x cubed plus x squared plus 3x between 0 and 3. And the other one will be 1/3 x cubed minus x squared minus 3x, and then evaluated between 3 and 6. Okay, plug this all in. 3 cubed divided by 3, this is minus 9. Then this is a plus 9, and this is a plus 9. If I sub in 0, I get nothing. Maybe I write plus 0 just so you can follow easier. And then 6 to the 3 divided by 3, so 36 times 2, which is 72, minus, and this would be 36, and then minus 18. And if I sub in the 3, I get a 9 and a minus 9 and a minus 9. All right, and so then we figure all this out and we get 36. So the area between the curves is 36. And 36 is a great number because it is the number on Tolo's jersey for his basketball team. Go Drillos! Go Drillos!